Thank you. Today, we go to the subject of the spacecraft exploration of Mars. Quite a different story from the exploration of Mars using ground-based telescopes that we talked about in the last lecture. The typical interplanetary spacecraft of the present time is a machine about as big as this lecture table. It may weigh half a ton or a ton, something of that sort. Is launched by a large rocket booster from someplace like Florida or Soviet Central Asia. Takes something like a year to go to Mars, about the same as it took British merchantmen to go to the Far East in the 17th or early 18th centuries. The spacecraft is unmanned. Unmanned missions are much less expensive than manned missions. They also are much more obedient. The spacecraft could fly by a planet. It could go into orbit around the planet. It could enter the planetary atmosphere. It could crash into the surface. There are some that are designed to crash. Most are unhappy if they crash. And there are then spacecraft designed to land on the surface of a planet. Mars has seen spacecraft fly by, spacecraft orbit, spacecraft crash, although accidentally, and spacecraft successfully land. Today, I'm going to be talking about the first space missions to fly by and orbit Mars. They were all called Mariner, and you can see there's some hint of that nautical exploratory tradition even in the name of the spacecraft. And the first was called Mariner 4, which went by Mars in 1965. Mariner 6 and 7 went by in 1969. And then the main subject of this talk will be what was found, the remarkable findings by Mariner 9 in 1971 and 72. This is a model of a typical such spacecraft. This is, in fact, the Viking orbiter. You can see the four big solar panels, look like panes of a windmill, that convert sunlight into electricity to power the spacecraft. There also often is a battery which can drive the machinery of the spacecraft during times, for example, when the spacecraft passes behind the planet and so cannot see the sun. The spacecraft receives commands from the Earth with a big radio antenna, and usually it uses the same antenna to send the data back via radio to the Earth. And all of the communication goes over this extremely long path, which may be as much as 50 or 100 or 150 million miles. The spacecraft has its own little rocket motor and fuel so that it can adjust its orbit, change its orientation, do things on the basis of what it finds. And then, of course, it has science. Here is a scientific payload which can scan. It's called a scanning platform, and it has the ability to follow Mars as the spacecraft goes by or orbits the planet. And here you can see two cameras, and there are many other instruments as well. The spacecraft typically could last for at least a year and maybe many years in working mode. The spacecraft is to some degree intelligent. It has a computer on board. It has pre-programmed instructions. It has a long list of stupid things not to do, which it constantly checks out. Am I doing something stupid? Am I doing something stupid? If it turns out that it is doing something stupid, it often knows how to correct that error. The computer can be reprogrammed from Earth so that the controllers on the Earth can decide to do something different. The controllers are in a large room in the United States at the Jet Propulsion Laboratory in Pasadena, California, and looking continuously at reports from the spacecraft about its internal health, how well it's doing, if any parts are failing, if it has enough power, if the temperature is right, and so on. And commands are sent from this command center. The commands go via land lines to a large radio telescope. This one is in the Mojave Desert in Goldstone, California. It is 85 feet in diameter, and it will send a coded radio message to the spacecraft at Mars. And the spacecraft knows how to read and interpret that information. Likewise, when the data is sent back, which it is on a regular basis, it is sent back to such a radio telescope, which then sends it to the scientists that are waiting in Pasadena for the data. There are such radio telescopes for the United States, not just in California, but also one in Spain and one in Australia, so that as the Earth turns, there is always a radio telescope pointing towards Mars to be able to get the data. Now, when Mariner 4 first flew by Mars in 1965, it took 21 pictures, the first photographs ever taken of Mars close up. And it could see things much smaller than could ever be seen from the Earth. It could see things a few kilometers across. And what it found, essentially the only thing that was visible in those pictures, were craters. And craters at that point became an important part of the study of Mars. Now, people know that the moon has craters. In fact, there are some craters on the Earth as well. And it was very interesting that an argument soon was raised that said, this proves that Mars has no life on it. And sometimes the argument went as follows. The moon has craters. The moon is lifeless. Mars has craters. Therefore, Mars is lifeless. Now, I hope that many of you will see that that is not a terrific argument. And you can imagine various arguments of that sort that don't work. My eyes are green. My nose itches. Your eyes are green. Therefore, your nose itches. And other arguments like that. That's not a good argument, but we heard it. In fact, we even heard the President of the United States, a Mr. Johnson, say that he was pleased to find that there was no life on Mars. And the reason that he was pleased was because he said that as a young man, he had been frightened by a radio broadcast about an invasion from Mars, which was based, in fact, on an H.G. Wells story of the same name, and that since he did not want an invasion, he was glad to find there was no one on Mars to do such an invasion. Well, this was an opinion which could be heard expressed by others, including the American divine Billy Graham, and shows that not only are there people who badly want there to be life on another planet, no matter what the evidence says, but there are people who badly want there not to be life on another planet, no matter what the evidence says. And the proper posture of a scientist, I believe, is to find out what's really there, independent of what people want. What we wish to be true is one thing, and it's important for our motivations. But what is out there may be quite a different thing. And it is always, I believe, important to be humble and open and questing in face of the truth. Now, the whole question of craters is an interesting one. What are the craters and how do they get made? We know that there are a large number of craters, let's say, on the moon. I'm going to come around here, and for a reason which you will shortly see, I'm going to put on this coat to protect me. Thank you. The solar system has lots of rocks in it. Big rocks, small rocks, medium-sized rocks. Some of them are in the asteroid belt, where they range up to several hundred kilometers across, and they are sort of worldlets. Now, today, most of these small and large rocks are on regular orbits, which don't intersect. Collisions are few. But at the early history of the solar system, when material condensed out of a cloud of interstellar gas and dust to form the sun and the planets, at that time, there must have been many more such rocks, and they didn't know they were supposed to be on regular orbits. So they did intersect, and there were enormous numbers of collisions. Now the solar system has been cleaned up by all these collisions, and they happen rarely. But in the case of, say, the Moon or Mars, we see signs of those early catastrophes. And such craters happen today as well. For example, Meteor Crater, Arizona, is about 1 kilometer across and was produced by an impact of a big rock falling from the sky. Big rock falls from sky, makes hole in ground. Easy to understand. The reason there are so few craters on the Earth and so many on the Moon is not that the rocks in the sky know they're supposed to land on the Moon and not on the Earth. Oops, I'm going to the Earth, I better move over here to the Moon. No rock knows about that. It's that the holes in the ground are rubbed out on the Earth better because we have running water, we have wind-blown dust. Those are erosive agents which can fill in and rub out craters. So just as many, more or less, craters are formed on the Moon as on the Earth, but the ones on the Moon survive because the Moon does not have many erosive agents, and the ones on the Earth disappear. So what often happens is something like that. Yes, I should warn the people in the front rows that this is going to be dangerous. And in fact, I shortly am going to call for volunteers, which will make it even more dangerous. So the rock falls into the ground deeper than the thickness of this tray and makes a hole bigger than it itself was. And sometimes there is a lip. Sometimes there is a central mountain. Sometimes a set of rocks fall from the sky simultaneously and make some sort of pattern. Occasionally there's a crater overlapping another crater. And there are lots of things that can be done. Also, it's fun. Sometimes rocks miss planets. That's all right. We have to have some rocks left. Now, I think I need some volunteers who will enjoy making a mess of the Royal Institution. Good. May we have you and you, and I need one more volunteer, you in the green tie. And be careful that you don't step on any asteroids. And what I would like you to do is to take some handfuls of marbles, it doesn't matter what the object is, and one at a time, but pretty fast, start throwing them onto the Moon. Might be Mars, and I'll join you. Okay, so... Okay, terrific. Wait, we have one sticking up. Good. Okay, I think we have made a good first step, but let's try a few more. Just, but don't throw. Let's just drop them in. Okay, we don't want to throw them hard because it'll destroy. That's right. Excellent. Good. Lovely. I'm going to now poke a few that are still sticking up down because there are no marbles to be seen on the Moon. And I'm not sure exactly what I will now do with this piece of Moon. Thank you very much. And I'd like to thank you for your help, because this is an important business of making craters on planets, and very few have a chance to do it. So maybe you can surrender your robes. Thanks. And I thank you for, oh, we have some asteroids left. Thanks very much. Now, let's take a close look. Mr. Coates can hold up a mirror at the results. And I think we got a lot of holes. Now, this is very close to what's called saturation cratering, where there are so many craters that one overlaps another, and you have hardly anything but craters and their debris. Now, that is the case in certain parts of the moon, but not in other parts of the moon. And I think it would be nice for us to spend a moment looking at the moon and seeing whether it bears some resemblance to what we've just seen. So now here is a photograph, in fact it's one we've seen before, of the moon. And the two major parts of the moon are the high, bright, heavily cratered areas, and the low, dark, lightly cratered areas. The latter are called maria, which is Latin for seas or oceans, because Galileo thought that these were in fact oceans. They are not. They are perfectly dry, bone dry. You can see a number of craters here, for example, is a dark crater. Here is one with a bright center. Here's another dark one. And as we look closer, we find tens of thousands of craters larger than a kilometer or so across. And a typical such crater is this one. We see the central mountain peak in the middle, which we did not find in any of our craters that we made in the Royal Institution a minute ago, but we understand the reason for that. It's produced by a rebound phenomenon, which could not have happened in this mud. We see the slumps at the crater walls, a kind of terracing. Sometimes there is debris which is thrown out by the impact. It is very similar to what we find in the laboratory. Now, the big basins on the moon, some of them are very large, many hundreds of kilometers across, are also produced by impacts, by bigger rocks falling. And I would like to show now a sequence of pictures showing how features on the moon probably formed. In the early history of the moon, in its final stages of formation, lots of rocks and debris were falling in, and there must have been an enormous number of craters to be seen. And here is an artist's view of how the moon must have looked in the final stages of its formation. But there were still some rocks to be acquired by the moon, and here is one in the process of hitting the moon, liquefying some of the surface layers, producing an enormous explosion, which then led to a multi-ringed crater, a sort of tidal wave, successive waves from the impact spreading out and then being frozen in the, as the lava, the hot rock, freezes. Then, either through the energy of the impact or through internal heating of the moon, molten rock welled up and flooded these lowland basins produced by impact. And here we can see the dark frozen lava, and also the little hint of red in the picture is due to another impact happening on top of this. Then you can see in this picture that the dark low regions have very few craters on them. As time passes, no new major events occur, but new minor events occur, and these maria accumulate, a sprinkling of additional craters over the following 4 billion years. Now that's a typical view of how major basins and craters form on the moon and on Mars. And so we expected there to be lots of impact craters on Mars. We had seen them from previous missions. And so when Mariner 9 was sent to Mars, we expected lots of craters. But the previous spacecraft had only looked at about 1% of the planet. So we didn't know whether all of Mars was covered with craters or if only small amounts of Mars were covered by craters. Turns out, as we will see in a minute, that something like half of Mars is heavily cratered and half of it is not at all heavily cratered. Now, what does it mean that a region is not heavily cratered? It means that it's young. It hasn't been around long enough to accumulate all these scars of ancient cosmic catastrophes. What does it mean that a region is heavily cratered? It means that it's old because it has been around long enough to accumulate all of these craters. So the cratered regions of Mars must be old, perhaps going back close to the beginning of Mars, about 4.5 billion years ago. And the uncratered regions must be young. As with the case of Phobos and Deimos, if we find craters, we can name them. And the only rule is that the people we name them after have to be dead. Fortunately, there are many dead people, and some of them even did some notable things in their lives. So in this particular region of Mars, for example, there are craters named Lowell, after Percival Lowell, who did a great deal for the study of Mars, one of the major ones of which is to excite 11-year-olds into thinking about Mars. Many of the generation of present planetary astronomers were first excited about Mars through Percival Lowell or Edgar Rice Burroughs, who wrote terrible romantic fiction based on Lowell's view of Mars. There is Maunder right here. He's a British astronomer who proposed that the Lowellian canals didn't exist. There are a large number of geologists, astronomers. There's a crater named Huxley, after Thomas Henry Huxley, who was a great supporter of Charles Darwin and gave lectures at this Royal Institution. There are even a few science fiction writers, including H.G. Wells, who have craters named after them on Mars. Now, when we arrived at Mars, when the spacecraft arrived at Mars in late 1971, we discovered that there was a planet-wide dust storm and virtually nothing could be seen on the surface of the planet, except in one place, a place called Tharsis, where we could see some strange features. And since this was the only place where we could see any features, we, of course, spent some time worrying about them. So here they are. You can see 3 dark spots or marks all in a row. Since you had 3 marks in a row, some of the more clever scientists proposed naming them Harpo, Groucho, and forgotten the name of the third, Chico, thank you. But reason prevailed, and they were called by appropriate scientific names North Spot, Middle Spot, and South Spot. The dark spot over here is exactly in the position of a feature which had been seen by 19th century observers and called Nix Olympica, the snows of Olympus. And such a lovely name that we called this spot Nix Olympica. But what were they? Well, the first thing we tried to do is to, with a computer, enhance the contrast of these pictures to bring out more detail. And you can see that that's what's being done, for example, here. Here is a close-up of Nix Olympica. Well, what do we see? We see a dark smudge which seems to have a hole in it. Now, let's pause just a moment before going on to these pictures and think, what does a dark smudge with a hole in it mean? Well, why are we seeing these features at all when the planet is covered with a great dust storm? The only thing which makes sense is that these are features sticking up above the dust. Well, what is a sort of roundish feature that sticks up above the dust? It must be a mountain. But this is a mountain with a hole in it. What is a mountain with a hole in it called? A volcano. Everybody knows that. Thank you. So this is the physicist's approach to figuring out what these things are. If you have a big mountain with a hole in it, it's probably a volcano. There is another approach to this problem. It's the geologist's approach, which is look closely at it, and if it looks like a volcano on the Earth, then it must be a volcano.
another good approach. So we attempted to look more closely at all of them. Here's an attempt to look at the computer-enhanced version of middle spot. And what do we see here? Another smudge with a hole in it. Well, the geological approach was frustrated for a while. Time went on, the dust storm dissipated, and eventually we got much better pictures of these features. And here, in the next picture, is an example. This is a close-up of middle spot. Ignore the rectangle, which is put on Mars by us and doesn't exist on Mars. And you can see this enormous mountain. Here is the base of it. Here it is going steeply up. Here is a big hole in the top called the caldera. It looks exactly like terrestrial volcanoes. Case proved. And here is a close-up of the largest volcano in the solar system, so far as we know, Nix Olympica, which is now called Olympus Mons, which means Mount Olympus. And whether there are any other famous individuals from classical mythology that live there as well, we do not know. But this is what Mount Olympus on Mars looks like. We are looking straight down the caldera, and let me describe what we have here. Here, on the right, is a flat plain here, which is the Tharsis Plateau. It is already very high. Here is a sheer vertical cliff, 1 to 2 kilometers high. Then we slowly walk our way uphill. The slope is modest here, very steep here. Then we come to the caldera, and there's a steep plunge in. Going to the other side of the caldera, we go down quickly here, slowly here, come again to the cliff, and go down to the Tharsis Plateau. From the base to the high point is almost 30 kilometers, almost 80,000 feet. It is a volcano which dwarfs, both in height and in lateral extent, any volcano on the planet Earth. And notice that there are virtually no impact craters. Here is one. There are almost no others. On the flanks of these volcanic mountains, they are therefore very young. A rough estimate makes them no older than hundreds of millions, perhaps a billion years old. You may think that's rather elderly, but it's young compared to the age of Mars. Mars is, in recent times, geologically active, which is very different from the case with the Moon, and shows, and there are many other things which show it, I'll come to them shortly, that Mars is by no means an object like the Moon. It is active in the sense that the Earth is. On the other hand, it has places which are very poorly eroded, like the Moon. It is a different place from either the Earth or the Moon. Now, volcanoes. We are going, this is Dirty Up the Royal Institution Day, and we have here a model of volcanoes. What is a volcano? Hot lava under hydrostatic, it was a rhetorical question, under hydrostatic pressure comes up a point of weakness in the ground, flows out, makes a mountain, and as the lava continues to flow up and overflow through the central caldera, the mountain continues to build. In the course of this, great clouds of ash are spread into the atmosphere and spread out on the flanks of the volcano. Well, we don't have really 4 volcanoes here, but we have a very good imitation of it. And if Mr. Coates will make the volcanoes go, we have a, you see, here's volcanic ash spilling out on the floor. Notice how the terrain is discolored and great cloud of smoke rising to the roof of the Royal Institution. If we were lit by sunlight instead of artificial lights, it would have gotten somewhat darker because the cloud of volcanic smoke would have prevented sunlight from coming in. Now, that happens when real volcanoes go off. They spread ash for great distances, they darken the sky, and they, in fact, cool the planet. And it is possible that in the time, 1 billion years ago or so, when the great volcanoes erupted on Mars, that there were substantial changes in climate which were the result of those eruptions. Now, I will come back to the question of climate change in a little bit, but right now I would like to go on to the next nice thing we found in the Mariner 9 mission. In looking at the polar caps, we found we could see them through the dust because they had high contrast. And here you can see 4 pictures of the polar cap. This is the south polar cap. The north polar cap looks very similar. And here you can see an outrider, a piece of frosted ground, which we see here in the 14th day of the mission, but here, by the 21st day of the mission, it has entirely gone. The cap is receding. The frost is vaporizing, going on into the atmosphere, going away. Here, if we take a close-up look at day 36, we see strange gulfs and gullies into the polar caps. And this is absolutely characteristic of the polar caps in both parts of Mars. And here we have an artist's impression of what it would look like close to the polar caps. And you see this sense of stacked plates, great poker chips piled one on top of another, each tens of meters high. And then off in the distance towards the horizon, another set of poker chips piled one upon another. These are features totally unlike anything we know on the planet Earth. The fact that there is a feature and then another feature after a pause, another feature after a pause for each of the poker chips suggests that on Mars there are events which turn on and off. You make a piece of this great laminated terrain, and then the process that makes it stops. Then after a while it starts again. Then after a while it stops. That sounds like changes in the climate, but on a massive scale, as if Mars is at one time balmy and another time ice age. And astonishingly, there is still other evidence suggesting that that's the case. Because as the dust storm really cleared, and we could see smaller, less obvious details on the surface, we discovered a range of extraordinary features that look like what we see here on the left. We here have a valley, but a valley with sinuosities in it. It meanders back and forth on itself. Also, a valley with tributaries. Here, for example, or in here. It looks very much like a river. And on the Earth, there are rivers which look extremely like this particular feature. This is the Red River in the United States, and let's compare it back again with Nergal Vallis, which is what this is called, on Mars. These features are remarkably similar in appearance. They seem to be produced by running water. Here is a quite different place of Mars with beautiful braided patterns and sinuosities, tributaries, collapsed banks, teardrop-shaped islands in the middle of the valley. It looks for all the world like a feature produced by running water. So now, having splashed mud on the Royal Institution and spread smoke and ash into the atmosphere, we now want to pour water on the floor. We have here an irregular surface. Imagine it on a much larger scale than it is, with great boulders and a strange source of water here. And now the water is going to move in some direction. Oh, look at that bifurcation, whatever it chooses to do. And we're going to let this run for a little bit and come back to it in a minute to see what the general configuration that it leaves is. If we look at rivers on the Earth while we're waiting, I hear an uncomfortable sound of running water behind me. I'll pay no attention to it. We see there are places where beautiful braided patterns exist. This is in the terrestrial Arctic. And there are other features which might look as if they were a river valley. This feature right here, for example. But it is not a river valley. It is a collapsed lava tube. Lava has made a channel for itself under the ground, and the overburden has collapsed, permitting us to see the course through which the lava flowed. This has sinuosities in it, but not tight meanders like terrestrial rivers often have. It rarely has tributaries. It is morphologically, in its form, different from terrestrial river basins. So we think it very likely that what we see on Mars is produced by running water. Now, if we can take a look, maybe with a mirror and me out of the way, at what we have made here, we see something which looks rather like a river valley. Can I just reach my hand in and point out this little island which has been left right here, which is a feature very much like that that we see on many Martian river valleys. What we never see is a thumbprint. Well, we now must come to the question of how do you make rivers on Mars? Because there is an aspect of the Martian environment which doesn't permit rivers to be formed, and that is that it is extremely difficult to have liquid water on Mars today. The atmospheric pressure is so low that if you had an open pool of liquid water, it would immediately evaporate and boil away. So it is very hard to have water around long enough to be able to carve a river which is hundreds, or in some cases 1,000 kilometers long. That suggests that the rivers, which weren't made yesterday, we can tell from their craters that they're quite old also, that the rivers were made at a time when the Martian climate, the Martian environment, was very different from what it is today. And that suggests massive climatic change on Mars. Now, at that time, we would have rivers forming. Here is a laboratory demonstration on a large scale, larger than we were able to do here, of water first flowing in a straight path, and then in a sinuous path, and then lovely braids forming. Well, there was a time in the history of Mars when that happened. That is probably not happening today. There was therefore once a time when Mars had higher pressures, higher temperatures, and abundant surface liquid water. That is when Mars was, in these senses, much more Earth-like. Today, Mars has a low atmospheric pressure, is on the average quite cold, has very little surface liquid water. It is in a deep ice age. Now, how can you have such a massive change in climate, even though it's over a period of hundreds of millions or billions of years? Well, the first thing to remember is that the Earth has had massive changes in climate as well. Here is a model of the Earth, and we have taped to the top of it the maximum extent of the polar cap at the time of the last great ice age, some 10 or so million years ago. And we can see that it's extended down quite far into Europe. London miraculously has escaped being covered by ice, but Chicago is buried under 2 miles of ice, which must make things uncomfortable for anyone who lives in Chicago some 10 or 20 million years ago. And today, by comparison, the polar cap is extremely small in the Arctic region, and all those places like Canada and Scotland are perfectly free of permanent ice. Now, how did that happen on the Earth? There are many views, and some involve the fact that the Earth has an orbit around the sun, and sometimes the Earth is closer to the sun, sometimes further. Sometimes the polar cap of the Earth is tilted more towards the sun, and sometimes further away from the sun. That's one possibility. Another possibility is that volcanoes on the Earth have made ash and fine particles in the atmosphere which prevent sunlight from striking the surface and cools the Earth. And there's a large number of other possibilities. In fact, there is a club of people who worry about how to make ice ages on the Earth. And to belong to this club, you have to invent a new reason. And there are, at last count, some 80 members. So you can see that there are lots of reasons proposed, and it's unlikely that they're all correct, although more than one could be correct. Now, in the case of Mars, there are similar possibilities. And let's just spend a moment on what those possibilities are. Here is a globe of Mars. Why don't we turn the sun on, always good to do when we talk about climate on a planet, and maybe we could dim the overhead lights a little bit. Good. Now, one possibility is that the sun itself gets brighter and dimmer over long periods of time. Let's see if we can dim the sun. Oh, good. There goes the sun dimming. Let's imagine great ice ages happening on Mars, the atmosphere condensing out at the polar cap. And now if the sun were to brighten up some, brighten sun, thank you, then we imagine the polar cap vaporizing, more atmosphere pouring into the air, enough pressure for water to run on the ground, rivers forming, and so on. Well, that's one possibility, because the sun might be a variable star. Another possibility is that there are times when the polar cap of Mars is pointed towards the sun, and at that time, polar cap vaporizes, more atmosphere, running water, and times when the polar cap is averted from the sun, and things get very cold up there, and all the atmosphere rushes away to freeze out in the polar regions. There are many other reasons proposed for climate change on Mars as well, and I've mentioned just a couple of them to give you some feeling for the kinds of events we're talking about. But these are grand events. They're on a planetary or solar system scale. It would be very nice to understand what they're about and to see whether causes of climate change on Earth and on Mars are similar or different. It might be that we could learn something about changes in the Earth's climate by examining changes in the Martian climate. Since we are poking about the Earth's atmosphere, making changes in the Earth's atmosphere and surface, it is possible that we might inadvertently, accidentally make major changes in the Earth's climate. It is important to study other planets as cautionary tales of what not to do with the Earth. Now, there is another consequence of these climate changes. If there was once a time when Mars was warmer with higher atmospheric pressure and more liquid water, doesn't that mean that there was once a time when Mars was more conducive to life of a terrestrial familiar sort than it is now? The Martian atmosphere, we knew by the time of the Mariner 9 mission, was composed mostly of carbon dioxide. The total pressure was only about 1% or a little less than it is here. It's about the same as the density of the Earth's atmosphere at an altitude of 100,000 feet. The air is quite thin on Mars. In addition, there are small quantities of water vapor, of, we now know, nitrogen, of oxygen, although much tinier quantities of oxygen. The amount of oxygen in the Martian atmosphere is much too little for us to breathe. And even smaller quantities, I'm dropping molecules, even smaller quantities of ozone, a form of oxygen which has 3 oxygen atoms. Now, this is actually not the best model of ozone. It does show 3 oxygen atoms. Now, could life exist in such an environment? What about the temperature? Well, the warmest it ever is on Mars is about what it is in this room, which is consistent with life, but a little on the high side. But that very night, the temperature would drop some 100 or 150 degrees Fahrenheit.
the temperature changes, say 100 degrees centigrade, 80 to 100 degrees centigrade. The temperature changes are enormous on Mars. There is not enough oxygen. The small amount of ozone has an important consequence. Because there is very little ozone, ultraviolet light from the sun penetrates through the Martian atmosphere to the surface. That doesn't happen here. We get very little of ultraviolet light from the sun because it's all absorbed by our ozone. If the ultraviolet light penetrated through the atmosphere, we would be in bad trouble, among other things because our hereditary material, our DNA, likes to absorb ultraviolet light and to fall to pieces and to make chemical bonds which are not consistent with accurate reproduction of the genetic code. Now, under these conditions, it seems that Mars is not a very likely place for life. But we can do an experiment. We can make a chamber which duplicates all of these Martian conditions, the temperature, the atmospheric composition, and pressure, and the ultraviolet light. Such chambers are, of course, called Mars jars. And we can inoculate the Mars jar with terrestrial microbes, bacteria, let's say. And when we do that, we find that lots of microbes do just fine. There are some that gasp and die for lack of oxygen. There are some that freeze to death. There are some that get fried by ultraviolet light. But there are many that enjoy those conditions extremely well. And if there are tiny quantities of liquid water available, say between little adjacent grains, they are able to reproduce. So the Martian environment is consistent even with some kinds of terrestrial forms of life, and therefore we should by no means exclude the possibility of microscopic forms of Martian life. That doesn't guarantee their existence, of course, but what we know about the Martian environment suggests that they might be there. And particularly if there were an earlier epoch when conditions were much more balmy, then perhaps the possibility of life on Mars is even greater. Now, this was one of the interesting conclusions from the Mariner 9 mission. In many people's minds, it had raised the likelihood of life on Mars. There was, among Percival Lowell's arguments for life on Mars, one which at least wasn't based on erroneous data, and that is that there were seasonal changes on Mars. We talked about some of them in the last lecture. Here is a different kind of seasonal change which he observed, and in fact which does exist on Mars. Here's the North Polar Cap, and you can see that it is surrounded by a dark collar of material which in fact follows it on its retreat each spring and summer towards the pole of Mars. Lowell thought that what was happening was that the polar cap was melting, wetting the ground, and that the moisture encouraged plants to grow and proliferate and darken the ground. The same idea was supposed to explain the seasonal changes, which we talked about in the last lecture. But Mariner 9 found a set of changes on Mars at all scales, big and little, which seemed not to be produced by vegetation, but rather by something quite different, by windblown dust. Here we have a nice region of Mars where the contrast between bright and dark markings is high. There's no frost here. And we're going to look at two regions. This one over here, which I will call the leaf. It's a big leaf. It's about 10 kilometers across. And this region, which is, as you see, serrated. There's another similar thing at the bottom of this crater, but we will not examine that. Now, here is a view of the leaf area, but with no leaf. And just 13 days later, we took another picture of this region, and there was the leaf. In less than 2 weeks, this major region, 10 kilometers across, developed. Now, could this be the growth of vegetation, or might it be that the dark area was obscured by overlying bright dust, which then blew away by the wind, revealing the dark material below? Well, if we now move to the serrated area and do a similar dissolve between before and after, which we can do with two television cameras here, we will see, I hope, that the
points at the bottom did a slight downward walk. And this serrated form and its motion is very typical of things which occur in laboratory experiments in blowing sand around. And we shortly are going to dirty up the Royal Institution in yet another way by blowing sand around. But before we do that, let's take a look at a laboratory experiment done under closer to Martian conditions than we will be able to, in which you see at upper left the wind blowing these little strings, and down here an originally regular pile of sand which has been made to take a serrated shape very much like that on Mars. Now here, and I have no idea how this experiment is going to turn out, we have a pile of sand on a dark surface, a wind machine, and we're going to turn it on and see what happens. So far, nothing is moving at all. Now we have streams of sand which are blowing down. We almost blew one of Mr. Coates's assistants away. We see long streamers which have come out. We have changed the initial configuration of the pile. Had we let this go for some longer period of time, we would have found that there were little outrider streaks like those that we see on Mars. We find, if we look elsewhere on Mars with the Mariner 9 mission, still further signs of wind-blown dust. Here, at left, we see a field of craters, and behind each crater is a bright streak, all pointing in parallel directions. And if we look at right, we see in quite a different place on Mars a field of craters, and behind each crater is a dark streak, all pointing in the same direction, although a slightly wider angle for the streaks that are dark than that are light. This looks very much like material at the bottom of a crater blown out by strong winds. All the craters had the dust blown out at the same time, and therefore all the streaks are parallel. Here is a lovely example of such a thing. This is a place called Mesogea, which means middle of the Earth, but it's actually on Mars. Here is a crater. There's a long, dark plume coming out of it. There's some source of dark material in the crater. But here is a place where the plume has not extended to. And we can see exactly why that has happened. The material blew out of the big crater and then was prevented by the walls or ramparts of this crater from falling behind it. What we see here, this bright feature, is a wind shadow. And such details confirm that we are seeing changes in the configuration of bright and dark features on Mars due to wind-blown dust. Now, almost certainly the changes that were seen by ground-based observers are due to weather and not to life. That does not exclude life on Mars. It just means that there was nothing that had been seen from the Earth on Mars that we now can say with any degree of reliability was produced by a Martian biology. Each time we look for something, we are a little disappointed, but each time we find something spectacularly interesting. In this case, here we have a map of the wind directions, which are deduced by these streaks and irregular features, and they give us a weather map of the directions the winds blew at the times of the highest speed winds on Mars. That is of great importance for the meteorologists, and in fact, it turns out that the weather patterns on Mars are quite like the weather patterns on Earth. They are comparable planets and have comparable weather. The fact that Mars has the same period of rotation, 24 hours, as the Earth, makes that comparison even more striking and bears out again a most important point about planetary exploration. There are certain sciences which are restricted to the Earth, or at least were until recently. Studying the weather was one.
studying climates, and climate change was another. Geology and geophysics is a third, and biology, the most important, is the fourth. Each of these sciences has been restricted to the Earth. The people studying these fields could not know to what extent their conclusions are generally true and to what extent they are anecdotal to the Earth. By extending our study to other planets, we are able to broaden the powers and generalities of these sciences and therefore to make them much more relevant back here on Earth. I believe that the entire effort at unmanned planetary exploration is more than justified in terms of cost on this basis alone. Now, I'd like to conclude by just showing you 3 more pictures found by Mariner 9, because there are many things found by this mission that we do not understand. Here is a photograph in Tharsis, the high plateau which contained the volcanoes. And there are many streaks which are behind craters, but there are some which are not connected with craters. In this region are a set of remarkably straight features, not connected with craters. And we can do a close-up of this region right here. And you can see how this streak, for example, does not begin in the crater. These little ones do not. And the manner of formation of these features is mysterious, but it may be due to what happens when very high-speed winds blow sand about, because the winds on Mars are much higher than the winds on Earth. Winds on Mars have been estimated at over 200 miles an hour, and in some cases up to 300 miles an hour, in fact, approaching the speed of sound on Mars. Over 100 meters a second to convert the lower number. That is a wind speed range that we simply don't know about on Earth, and maybe there are strange patterns that occur in that case. Even more mysterious, and this is something I love to show, are these features found by Mariner 9. You can see here are 2 mountains of pyramidal shape. They are oriented in the same direction. They are each 3 kilometers across at the base, 1 kilometer high, lovely sculpted objects. What are they? That is also a rhetorical question because no one knows the answer. If we take the typical geological approach, which is if it looks like something I know about, then that's what it is, I guess we would have to conclude the existence of Martian pharaohs. That seems to me a little premature, risky, not the only possible conclusion, although it would certainly be terrifically interesting. Because there is something else which happens on Mars, and that is sand blasting. The sand, which is carried by these enormous winds, can erode and rub down and carve out mountains which are previously irregular. And therefore, over 10 or 100,000 years, the high-speed winds on Mars might have carved 2 or more quite irregular mountains into these lovely quasi-pyramidal shapes, which we see in this particular region. Maybe that's not what's the cause. Maybe something far more exotic is. We are by no means sure. Mariner 9 has revealed mysteries. It has solved many old problems. It has raised many new problems. To really investigate these problems, we must go even closer to Mars and land on the planet, and that is the objective of Viking next lecture.